NMR spectroscopy, or nuclear magnetic resonance spectroscopy, is one of the most important tools that we have for identifying organic structures from an unknown organic liquid. Now, in order to correctly interpret an NMR spectra so that we can identify what organic compound we have, we need to use three key things. We're going to use the chemical shift. So chemical shift tells us something about the environment of our atoms within our molecule. We need to look at the integration. The integration looks at how many hydrogen atoms we might have in a particular chemical environment. And finally, we need to look at splitting. So splitting is going to allow us to look at the connectivity between these different atoms so that we can start to piece together what our organic structure looks like overall. Let's start by looking at chemical shift. So chemical shift, again, looks at the chemical environment around our individual nucleus and how that affects the signal that we receive from our NMR instrument. Now, as you should recall, so our NMR signal, so for hydrogen NMR, which is our most common NMR, we're looking at the spin of our nucleus. We add an external magnetic field. So this is going to be B0. And this creates two different energy levels. We have a high energy state and a low energy state based on whether our nuclei is aligned, the spin of our nucleus is aligned with that magnetic field, or whether it's aligned in opposition to that magnetic field. Now, when we add our little electrons in here, so every hydrogen atom has an electron that will orbit that hydrogen atom, and our electron is going to add another magnetic field, our BE, the magnetic field from that electron. And so we can look at our effective magnetic field as our external magnetic field minus that magnetic field from our electrons that's opposing our external magnetic field. Now, if we look at an organic molecule, so let's say we have a small alcohol. So we have, I'm going to go ahead with a 3-carbon alcohol. So here's our 3 carbons. Now we have our oxygen attached to one of our carbons. We have some hydrogens here, some hydrogens over here, and 3 more hydrogens at this end, right? As usual, every carbon has 4 bonds in order to get that complete octet. Now, again, we want to specifically look at our hydrogen atoms, right? Our NMR technique is specifically looking at the 1H hydrogen nucleus. There are other NMR techniques that can look at other atoms, but right now we're going to specifically focus on proton, or H1 NMR. Each of our hydrogens in this molecule has a single electron that it's using to form a covalent bond with a carbon. Right? Those are all of our bonds in here that we represent with our straight lines. So you might think that they would all have the same magnetic field associated with those electrons. However, this is not the case. So remember, our electron density in our molecule overall is strongly affected by the positioning of our atoms within this molecule. If we have electronegative atoms, they'll pull electron density towards them and away from other atoms in our molecule. Now, as we look at our structure here, so our oxygen is, of course, quite electronegative. So we have our electronegative oxygen, and it's going to be pulling electron density away from our other atoms and towards that oxygen. Right? We usually represent this with a little partial negative charge on the oxygen, and a partial positive charge on the atoms that it's bonded to. So, of course, in this scenario, we would expect this hydrogen right here would have electrons pulled away from it, right? So we can say this has low electron density. And so, because it has low electron density, that means we have a low magnetic field created by those electrons, a decreased magnetic field. And so that means we have a higher effective magnetic field. Or we would also say that this is a shielded, or a deshielded rather, a deshielded nucleus, because we're pulling away those electrons that would normally shield our nucleus. Now, because of that, we're going to have a higher effective magnetic field creates a larger energy gap, right? So if we add this particular hydrogen to our diagram, we'd expect that its energy gap is going to be larger compared to a typical hydrogen atom, right? That has its fair share of electrons. This hydrogen has less than its fair share of electrons because the oxygen is pulling electrons away. So we create a larger energy gap, right? Remember, our energy gap, delta E, is the distance between these two energy levels, and this corresponds to a higher frequency is required for our nucleus to absorb that radio frequency from our NMR instrument. So we'd expect this hydrogen to have more deshielding from the oxygen pulling away electrons. It would have a higher effective magnetic field and therefore a higher frequency overall. Now, if we look at our other hydrogens here, so all of these hydrogens, right, they're just attached to carbons, right? Our hydrogen-carbon bond is effectively nonpolar, right? There is a slight difference in electronegativity, but generally we just like to exclude that in organic chemistry because it's very minimal. So all of these hydrogens should have the same effective magnetic field, right? Wrong, right? Remember, whenever we have an electronegative atom in our structure, right, that oxygen there, it's going to exert an inductive effect on our entire molecule, right? We show our arrows pulling electron density from adjacent atoms, but in reality, the electron density on our molecule as a whole is pulled over towards that oxygen. So all of these hydrogens are going to be somewhat deshielded by that oxygen. Now, how do we know which hydrogens are going to be most deshielded? Well, as we know with inductive effects, the closer that electronegative atom is, the stronger the effect is, right? So our deshielding will decrease as we move to the left, right? These guys will have relatively little impact from the oxygen on the far side of our molecule. These hydrogens will have a little bit more, and then these hydrogens will have more than that, right? As we go closer to the oxygen, we'll see more deshielding, therefore a higher effective magnetic field and a higher frequency. So if we go ahead and label our hydrogens, so these three hydrogens are all the same, so they're going to have the same overall effective magnetic field, right? They're attached to the same carbon. They see the same exact chemical environment. So we'll group these all together as one, so that we'd say that these are our equivalent protons because they experience the same chemical environment when they're all attached to that same atom. These hydrogens here we'll group together. This is our group 2. These two are attached to the same carbon. They see the same chemical environment. And this will be group 3. So if we compare our groups in terms of energy levels, so 3 would be the most deshielded, have the largest gap. 2 would have a somewhat smaller gap. And 1 would have the smallest gap of all. Right? The level of shielding is decreasing as we move towards 3, and therefore experiencing that higher magnetic field, and it then is requiring a higher frequency to match that larger energy gap. Now, how do these energy gaps actually apply to what we observe in our NMR spectrometer? Now, our NMR spectrometer doesn't show us those energy gaps directly, right? What it does is it sends a variety of different frequencies of electromagnetic waves, and it sees which frequencies are absorbed based on what those actual energy gaps are. So let's look at what a typical spectrum might look like based on these differences in chemical shifts. So our NMR spectrum is going to come out. We'll have our y-axis is just the intensity of the peak, which we'll talk a little bit more about that later. The x-axis is going to be the frequency, which of course relates to the size of that energy gap. All right, so let's see what our NMR spectrum would look like then based on the energy gap pattern that we've already described. So here's our frequency axis. We'll have our high frequencies over here on the right and our low frequencies over here on the left. So now remember, in terms of energy gap size, we went from the largest over here for this one. I'm neglecting the hydrogen directly attached to the oxygen right now. And this had the smallest, right? So that's because this one is most deshielded by our oxygen, and therefore it has the lowest magnetic field from the electrons, and therefore the highest effective magnetic field. So with that highest effective magnetic field and that largest energy gap, we would expect our largest frequency over here. So let's go ahead and put that peak on. So we get our hydrogens. Both those hydrogens absorb at the same frequency since they have that same chemical environment. They are equivalent hydrogens. And we get a peak here at our higher frequency area. Now the next peak, it's slightly less deshielded because the oxygen is farther away. So its frequency is a little bit more, lower because there's more electrons around blocking that external magnetic field. So put that at a slightly lower frequency. And now number 1 has the lowest frequency of these 3 groups of hydrogens because it's the most shielded. It experiences the deshielding of that oxygen the least. So we get 3 different peaks. Again, this is the peak from the hydrogens number 1, that group of equivalent hydrogens, number 2, and number 3. Right? As we get closer to an electronegative atom, our frequency gets higher because we're more deshielded. So this is one of the first things that we can use to start to learn about our compound from our NMR spectra. Right? The positioning of our peaks tells us what our chemical environment looks like, how much it's deshielded by other electronegative groups versus how many electrons are around it, shielding it from the external magnetic field. Now, right now, I'm showing this as a graph based on frequency. Now, the problem with frequency is that, remember, that frequency also depends on the external magnetic field. Right? So if we go back to our equation, we had our frequency relates to, of course, the effective magnetic field, which relates to our external magnetic field minus the magnetic field from our electrons. Now, if we use a different NMR spectrometer, this can actually change what magnetic field, external magnetic field, we experience. So this will vary from spectrometer to spectrometer. So if we report just the frequency, then it's hard to know for sure what that chemical environment looks like. Right? Our frequencies will all be very high if we have a very strong magnet, or our frequencies will be lower if we have a weaker magnet. So in order to counteract this, what we do is we use a standard that we can then always relate our frequencies to. So the standard that we normally use in NMR is TMS. This is tetramethylsilane. So as the name suggests, so silane refers to a silicon atom at the center of this molecule. And then we have 4 methyl groups attached to that silicon. All of our hydrogens here, so we have 3 hydrogens on each of our carbons. These each have the same chemical environment, right? So note they're all attached to a carbon that's attached to a silicon. So we can say these are all equivalent, and we'll just have one signal from this molecule, right? All of our hydrogens see the same chemical environment, and so they'll all have the same energy gap and the same frequency. Now, silicon, of course, remember, is lower on the periodic table than carbon, so that means that carbon is more electronegative, so we will actually end up pulling electrons toward our carbons. That means that we'll have a relatively high electron density around our carbons and then also around our hydrogens as well. So our hydrogens will be very shielded in this molecule. So if we're going to add this TMS, or tetramethylsilane signal, onto our NMR spectrum, we would expect that it would show up somewhere down here. Right? So it's going to be more shielded than anything else. Right? It tends to be one of the most shielded, and therefore the lowest frequency peaks that we observe on a typical hydrogen NMR spectrum. So now we have our TMS standard here on our graph. So this is our TMS. But our graph is still shown based on frequency. So what we're going to do is we're going to take each of our signals, right? So I'm going to take the frequency of signal 1. So frequency of 1. And I'm going to subtract the frequency of my TMS, right? So I'm going to basically look at where my peak is relative to the TMS. And then I'm going to divide that by my spectrometer frequency. So I'm actually going to express the strength of my magnetic field in terms of frequency so that I can cancel out my units of frequency and I obtain a new term of chemical shift. So my chemical shift, this is usually represented using the little Greek letter delta, and we usually express this in ppm units. So normally our NMR spectra are going to use chemical shift in ppm. We will have a TMS standard, and then we'll just have all of our peaks compared relative to that standard. Right? By dividing it by my spectrometer frequency, I've eliminated the frequency from my equation, and now I can just look at where my peak is at, so whether it's shielded or deshielded relative to that TMS standard. So now we can replace that frequency on our graph before with our chemical shift. So our TMS standard is always going to be at 0 chemical shift, 0 ppm. So obviously, of course, if you took the frequency of that TMS signal and subtracted itself from it, you're always going to get 0, right? Since that's your standard, it will always be at 0. Now, as our frequencies, so remember this, our frequency on here, right, started at low values and went to high values. So this was a lower frequency. Now we go to a higher frequency. We subtract a lower frequency from a higher frequency. So our chemical shift is increasing relative to that TMS, right? So this will be going from low to high chemical shift, just like we went from low to high frequency. So now we have our graph expressed in terms of chemical shift. Our TMS, of course, is always going to be at 0 ppm. This is our shielded TMS, right? It's shielded because we have that extra electron density on our hydrogens as those carbons are pulling electron density away from our silicon. Higher chemical shifts are going to be more deshielded. And of course, this also relates to our frequency as well, right? This would be low frequency or low energy gap, and this would be high frequency, high delta E. So this is what our typical NMR spectrum would look like. Normally we actually flip this graph and we actually put our 0 on the right-hand side and we go towards more deshielded on the left-hand side. So now here you can see I've rearranged my graph into the typical arrangement that we use for an NMR spectrum. So my TMS now is over here on the right at 0 ppm. So again, this would be my most shielded. And now as I move to the left, my chemical shift is increasing as I'm becoming more deshielded. Again, this corresponds to higher frequencies and lower frequencies. You also see these signals that are at lower ppm values referred to as upfield. So this is because, of course, our magnetic field from our electrons is stronger at those lower chemical shift values. And our peaks over to the left are then downfield. Now these general chemical shift trends will be the same for all organic molecules, right? So we'll have our lower chemical shift values for more shielded hydrogen atoms, and we'll have our higher chemical shift values for more deshielded hydrogen atoms, all based on where they are in our molecule and where other electronegative groups are in relation to those individual hydrogens.